In this video, we're going to look at the ratio test as yet another tool that we can use to potentially determine convergence or divergence of an infinite series. And the ratio test is kind of built on the idea that if I have an infinite series, a sub n, that as n goes to infinity, the series possibly behaves like a geometric series. Now, we're not saying that it is a geometric series, but that as n gets closer and closer to infinity, the terms start behaving like a geometric series does. And so we can use what we already know about geometric series to determine if this particular series converges or diverges. So I want to start with a geometric series. And if we wanted to determine if this series converges or diverges, you know that we need to know the common ratio. And as I've written the series here with fractions being reduced, it's kind of hard to just look at these fractions and tell what that common ratio would be. But I know that if I already know it's a geometric series, I know that there is something I'm multiplying every time to generate the next term in the series. And so to find that term, I can pick a term in the series, like say the 1/2, and I can divide it by the term that comes before, and that will give me the common ratio that I'm looking for. So I'm going to multiply by the reciprocal here, and I get 3/4. I could have done this with the 3/8 as well. If I'd picked the 3/8, I could divide by 1/2 and multiply by the reciprocal, and we get 6/8 or 3/4. And of course, that common ratio is going to be the same because we were told in the beginning that it's a geometric series. Now, what I want to point out here, if I label the terms of my series, I'm going to call this a sub 1, a sub 2, a sub 3. What I did the first time here in calculating r is that I took a sub 2 and divided it by a sub 1. I divided by the term that was before it. The second time I calculated r, I used a sub 3. I divided it by the term before it, a sub 2. In general, if I want to calculate the common ratio in a geometric series, I can take the n plus 1 term and divide it by the term before it, which would be a sub n, and that would give me the common ratio. So I review that because this is a big part of the ratio test. Here's the test. If we have this series, and I'm going to add a note here that these need to be positive terms eventually. You could have a series where the first few terms are negative, but eventually all these terms need to be positive in order for the ratio test to work. The first thing that we're going to do is calculate the ratio, and I'm going to use a capital R here because this little r is what we are using for the common ratio when we have a known geometric series. It's the common ratio, the same ratio every time. Here I'm using capital R. This is representing a ratio of one term to another, but it's not necessarily common all the way throughout the series because this is not necessarily a geometric series. This common ratio is going to be equal to the n plus 1 term divided by the nth term. We're still going to calculate the ratio that way, but what I want to do is take a limit of that ratio as n goes to infinity. Because the idea here is really only working as n is approaching infinity. Once we have this common ratio calculated, here's the analysis for the test. If that common ratio is between 0 and 1, including 0, not including 1, then the series converges. Just like with the geometric series, if our common ratio is less than 1, our geometric series converges. Same is true here with the ratio test. If that ratio is between 0 and 1, then the series converges. If that ratio is greater than 1, then the series diverges. Again, similar to the geometric series test. Here's the difference. Notice here that I have not included 1 in either of the inequalities. If that common ratio equals 1, then this test is inconclusive and we have to use another test. And so you shed a tear because you have to do more work. So let's look at an example. Let's say that we have the infinite series 10 to the n over n factorial. And I will make a note here that whenever we have factorials in the expression for our infinite series, the ratio test is your choice for determining convergence or divergence. If you've got factorials, ratio test is the way to go. First thing that we're going to do here is calculate that common ratio. It's going to be the limit as n goes to infinity of the, and I'm going to kind of do this backwards. I'm going to start with the nth term down here on the bottom, which is just the expression that we have. The n plus 1 term is going to be 10 to the n plus 1 divided by n plus 1 factorial. Again, what we're doing here is we're taking a term and dividing it by the one before to determine the ratio between the terms. This is a sub n plus 1 divided by a sub n. Now, we are dividing fractions here, and so we're going to multiply by the reciprocal. And I will say in the future, if you want to skip writing out this step of the division and just go straight to multiplying by the reciprocal, that's totally fine. I certainly wanted to show the step here to reinforce the ratio that we're forming here. But to divide it, we are going to multiply by the reciprocal, and you can go straight to this step. So now what we need to do is simplify what we're looking at here. See what we can divide out to make this expression simpler so that we can determine the limit. So I see that I've got 10 to the n plus 1 divided by 10 to the n. Whenever we divide like bases, we're going to subtract exponents. So n plus 1 minus n would just leave me with 10 to the 1 up here. Like all of those are going to divide out, and I'm just left with 10 to the 1. And then the factorials, I've got n factorial over n plus 1 factorial. And let me just give a little reminder of how to divide out or simplify factorials. Let's say that I had 6 factorial over 7 factorial, which is how these two expressions are related. Like the one in the denominator is just one more than the number in the numerator. So the numerator here is, of course, going to be 6 times 5 times 4 and on down to 1. The denominator, 7 factorial, is 7 times 6 times 5 times 4 and so on. So notice all of the 6 factorial is going to divide out, and I'm just going to be left with the 7. What that means here is if I have n factorial and n plus 1 factorial, the n factorial is going to divide out with this factorial, and I would just be left with n plus 1. So then after all of that, this is equal to the limit as n goes to infinity. In the numerator, I have 10 left, and in the denominator, I have n plus 1 left. This work that we did right here in this step, I think that's the hardest part of the ratio test, is doing all of this simplifying to get it down to an expression where you can easily evaluate the limit. Now I can see if n goes to infinity, my denominator is going to get very large, which means my fraction is going to get very small, and it's going to approach 0. Now, once we have the limit calculated, we always want to compare to 1. Is this number greater than 1, equal to 1, or less than 1? And in this case, 0 is obviously less than 1. And if you remember from our analysis piece, that means, therefore, that my series converges. I'm going to do one more example for you. Let's say that we have 1 over n squared plus 2 is an infinite series. I'm going to start out by determining, setting up the common ratio. Limit as n goes to infinity of the, and this time I'm going to go straight to the multiplying by the reciprocal part. I'm going to start with the n plus 1 term, 1 over n plus 1 squared plus 2. So I just changed my n to n plus 1. I'm going to multiply by the reciprocal of the nth term, n squared plus 2 over 1. And you may be able to evaluate that limit just looking at this. There's nothing we can divide out here. I've got, we're adding n squared to the plus 2. This is a totally different base being added to something else. There's nothing we can divide out here. And you could evaluate the limit in that form. I'm going to go ahead and multiply this out down here, because I think it makes it really easy to see that as n goes to infinity, I've got n squared over n squared, and same power in the numerator and the denominator. And so this limit is going to be equal to 1. And in that case, since this equals 1, therefore the test is inconclusive. And we need another test. We need to use another test. The appropriate test to use on this series, or an appropriate test to use, would be one of the comparison tests, which we will be learning in the next video.